Okay, once again, my name is Lance Zurich, and I'm the product manager for the fischertechnik division over here at Studica. And today I'm going to provide you with an overview of some of the areas of STEM and technology that you can explore with your students by using the fischertechnik education system in your classroom. Now, for the purpose of today's presentation, we're going to focus specifically on the 7 sets which currently comprise the fischertechnik STEM fundamentals line, which was designed for use in middle schools, high schools, and colleges. So first off, the question that might come up is, what is fischertechnik? Well, just to provide you with a little bit of background, fischertechnik is a flexible and innovative construction system. Now, unlike other popular construction sets that are designed to simply stack, fischertechnik was created with more of an engineering mindset. And the reason I say that is that the core building block in the fischertechnik system is unique in that it allows attachment from all 6 sides, and thus it allows for almost limitless design possibilities. Now, many of the parts are designed to slide together and lock in place using friction, and the hundreds of different parts available also will help you to address very specific design needs. Now, fischertechnik was created back in the 1960s by noted German inventor Arthur Fischer, who's known for countless innovations used in the construction and the automotive industries. Mr. Fischer, at the time of his death in 2016, held more patents in his name than Thomas Alva Edison. Now, besides fischertechnik, Mr. Fischer was the inventor of synchronized flash photography back in 1949, and he was also the creator of the expanding nylon wall plug, which is used in conjunction with a screw or a bolt to help anchor heavy objects to walls. His company, the Fischer Group, employs thousands of people worldwide, producing many variations of fastening devices used in building construction, as well as many components used in the automotive industry, and they also provide consulting services. I'd also like to mention right here at the top that fischertechnik was the very first construction set to offer students the ability to build and program their own robots using the original pre-Macintosh era Apple computers. Now, almost since its inception, fischertechnik has been used by middle schools, high schools, colleges, and universities all around the globe to explore STEM-related concepts. These are, of course, things such as robotics, renewable energy, mechanics, pneumatics, and much more. Fischertechnik has also been used by numerous companies like Porsche, Daimler Chrysler, and BMW, just to name a few, for industrial simulation and training purposes. Now, recently, we've also seen many of the top companies at the cutting edge of developing IoT applications, also known as the Internet of Things, using these same simulation and training models to demonstrate and study various IoT-related processes. Now, as such, more than being just something that students are only going to use for a year or two in their development, fischertechnik is really designed so that students can grow along with it. As students progress through their academic careers, they can also progress through the various levels of fischertechnik education solutions which are available. Fischertechnik education products are designed to offer a progression. And what I mean by that is at the elementary level, specifically grades 2 through 5, there are curriculum-based options for introducing brief, achievable activities based around simple machines, as well as introductory robotics and coding. Now, when we get to the middle and high school level, there are sets for performing various different STEM-related activities around a progression of subject-specific models, which can then be inserted into class activities as needed. Or, if you wish, there are also more extensive standards-focused curriculum sets available for offering a complete and fully integrated project-based STEM experience as a class unto itself. Now, for college classes focused on robotics and automation, or for vocational and technical schools, there are also a series of pre-assembled industrial training and simulation models. Now, while the subject matter may become more advanced and sophisticated as you move through these levels, the same building system and the same essential parts are used throughout all levels. Now, here we'll see a list of the various product lines that fall under the banner fischertechnik education in order of how they appear in the progression we just discussed. Now, for the purposes of our presentation today, we will focus on the area highlighted in red now, the STEM Fundamentals series. Each of these sets is designed to focus on a particular subset of what we refer to as STEM, and will include instructions for building a specific progression of models related to that area. Now, please note that these sets, while all educational in nature, do not contain formatted curriculum. Instead, each contains either printed teaching and activity materials or provides access to downloadable versions of such materials. This material is designed to provide teachers with suggestions for various experiments and tasks that students can perform with each finished model in class. There are currently 7 different sets in the STEM Fundamentals series, all of which you will see listed here on the screen. Again, each set concentrates on a specific STEM-related topic area such as electronics, optics, or renewable energy. These sets are designed so that they can easily be used in middle and high school settings, but there is no reason that they cannot also be used at the college level when exploring these same topics. Each set comes packed in a sturdy plastic gratinol storage box, and besides the teaching and activity material I mentioned, each, of course, comes with a printed, full-color, step-by-step assembly manual for building all these models. In all cases, with the STEM Fundamentals line, everything you will need, aside from either a 9-volt battery, or if you prefer, a rechargeable fischertechnik AccuSet battery pack, is included in each of these sets. Now at this point, let's get started by first off looking at the Mechanic 2.0 set with a part number of 538423. This set is used for exploring different aspects of mechanical engineering, and it's an upgrade version of an earlier set simply called Mechanics, and contains several sophisticated new models. In all, this set contains 500 parts for building 30 different models. Topics addressed by the Mechanics 2.0 set include the following: understanding the concept of mechanics, the effects and forces which affect rigid and moving bodies. Dynamics. When machines or gears are set in motion, they are referred to as being dynamic. Dynamics describes the change of the movement variables such as the rotation of the shaft. Electric motors. Students learn how electric motors are used in machines and also about revolutions per minute and gear units. Gears are explored in depth. There is an overview of the various types of gears that can be used, such as worm gear pairings, toothed gears, and crank gears. Students begin by building very basic gear models using each of these different gears to learn the principles behind them and their specific functions. They will also learn about and work with transmission ratio, torque, inclined planes, and various vehicle drives. Steering systems using axle pivot steering and fifth wheel steering are explored and compared. Next, students will build and study models of a compound gear unit, a planetary gear, and a bevel gear unit. Students then experiment with the differences in speed and direction when shifting from one gear to another in each, and they learn where such gears are commonly found. Students will also build a model of a kitchen mixer which combines both a bevel gear and a planetary gear. Students will learn how a differential gear is used, why it's important, and will build a working model to study its function. Next, they will construct a scissor elevating platform to learn about screw spindles, joints, and levers. A windshield wiper model which will be used to study how a crank rocker gear unit transforms a rotational movement into an oscillating, of course back and forth, movement. A 4-bar chain unit will be built next so that students can study its 4 joints and how the components interact and move. A hacksaw machine will be used to help students understand how a coupler mechanism works. Levers are studied with the use of a beam and scales. A scale with a sliding weight is used to experiment and understand torque. And a lifting tackle with pulleys is used to understand physics' golden rule, which is the concept that work cannot be saved. Whatever is saved on force must be added in time and distance. Next, the focus of the activities moves to the area of statics, the conditions under which the forces of a body are in balance. Stability and bracing is addressed by showing the way a simple 4-legged table is braced using the concept of statical triangles, as well as how a double-sided ladder is designed. Next, the fundamentals of bridge design are explored, starting with a very simple girder bridge. Next, students build a modification where an underbeam is added, then a third bridge with an upper beam. And finally, a cable-stayed bridge. Students will learn why bridges are braced in these different ways and how the weight loads they will bear and the distance they must span play into this decision. Finally, students will integrate what they have learned about mechanics, levers, and statics with the construction of these previous models for the building of a working crane model. Students will complete several tasks and record their observations. Now here are a few samples from some of the pages of teaching materials used with this set. Please note that this teaching material shown here is not in a printed format, but is instead downloadable. The printed assembly manual included with this set will include directions and a password for downloading these materials directly from the fischertechnik e-learning portal. And that's the Mechanics 2.0 set. I should also mention at this point that all of these sets that we will discuss in this segment are recommended for use by groups of 1 to 2 students at a time. If you increase this number, when building some of the more basic models, you run the risk of having students sitting idle and just watching, while other students do all the work. So to keep everyone engaged, we recommend staying close to this number as often as possible. Next, we move on to the fischertechnik Educational Electronics set. Now this set is designed to offer an engaging introduction to the fundamentals of electrical engineering with a focus on the areas of analog electronics, digital electronics, and the logical functions of digital electronics. The set contains 260 parts along with detailed instructions for building 16 different models. Students will begin by learning about circuits, both by creating schematics with the use of standardized symbols and by working with actual circuits. They will begin first by building a simple circuit, and then moving on to exploring open and closed circuits by incorporating the use of a push button that can either connect or interrupt the flow of electricity. This is studied with the use of models simulating a flashlight and refrigerator lighting. Students will also learn about conductors and non-conductors by using a continuity tester. Next, students will explore series and parallel connections, also known as and/or connections. They will build several models to experiment with both series and parallel connection variations. A simulation of hallway lighting is used next to provide an example of a circuit with 2 three-way switches, sometimes referred to as single pole double throw or SPDT switches. Next, students will experiment with 4-way or double pole double throw DPDT switches by using a merry-go-round simulation with a pole reversing switch. Students will also learn about a selection of electronic components and how and why each is used. This includes things such as resistors, capacitors, light-emitting diodes, transistors, and phototransistors. Now the schematics you see here and on other slides in this section are taken from the teaching and activity guide, which in the case of this particular set is an actual printed guide which is included inside each box. Students will then begin to incorporate these components into a selection of models for hands-on experimentation, including variations on a flasher and a touch switch. Next, an element of computer automation is introduced with the use of a small pre-programmed electronic module, which is combined with the previous merry-go-round model for further exercises. Students learn about inputs, outputs, and using the DIP switches to select different programmed actions. A light barrier and a touch switch are added for more variations. Further activities with the programmed module are conducted using a simulation of a ship seesaw, as well as an alarm system simulation. And at this point, another component is introduced, the negative temperature coefficient thermistor, which is also known as an NTC resistor. Activities are performed with this new component using simulation models based upon both a ventilating fan, where the hotter it gets, the faster the fan runs, and a bathroom fan that is designed to turn on when a light is switched on. The final model addressed in this set is a simulation of an automated sliding door, which combines light barriers acting as proximity switches with touch switches. And that's the overview of the electronics set. Once again, the set includes 260 parts, printed instructions, and activity booklet, and is designed for use by 1 to 2 students at a time. The next set in the STEM Fundamentals series is Optics and Light. This set enables students to explore various optical phenomena such as refracting light, reflecting light, and the interplay of shadow and light. The set contains 270 parts for constructing 15 different models used to illustrate the science of sight and light. Students will begin by learning about bending or diverting the direction of light, which is known as refraction. To do so, they will build and work with two different magnifying devices, one with simply a single lens and one that adds a light to it. Students will learn how the addition of light increases the contrast between light and dark points, and by doing so, causes the object being magnified to appear in sharper focus. They also learn how thicker lenses have a shorter focal length than thin lenses because of how they refract light to a greater extent. Further experiments are conducted with magnification. Students build a slide viewer, such as would be used to view old 35mm photographic film slides. A second lens is added for the building of a microscope simulation, where students learn about the difference between transmitted light, where light shines through an object, and the reflected light that sharpens what is being viewed. Students will also switch the lenses used to observe how this can increase the magnification factor. The next activities center around viewing objects that are farther away. Students will first build a two-lensed erecting telescope and learn how to calculate the telescope's magnification factor by dividing the focal length of the objective lens, the one at the farthest end of the telescope, by the focal length of the ocular lens, the lens closest to the viewer's eye. What the students will find is that by only using an objective and an ocular lens, objects far away appear upside down. As such, students will next build a second telescope variation called an erecting telescope, which incorporates a third lens, referred to as the reversing lens, between the objective and ocular lenses. Now they will find images are viewed correctly. The reflection of light will be the next topic explored with the use of a mirrored course model. Students will observe the pathway of light and learn about the law of reflection, which states that the angle of incidence equals the angle of reflection, a principle that is applied to the design of optical instruments such as single-lens cameras and video projectors. Next, a periscope is built, which uses an objective mirror and an ocular mirror in place of lenses to view things from around a corner. We then move into the area of shadows and light and how a sundial is used to tell time. Another model is used to show the two shadow areas, partial and full shadow, that occur during the phenomena of a total solar eclipse, as many people in parts of the U.S. had the chance to experience the other summer. The subject is further explored with the use of a planetary model to understand the phases of the moon. Different light effects are examined next. Students are told about the experiments conducted by physicist John Tyndall back in 1870 when he was able to send light through a stream of water. This is related to the use of a fiber optic cable, where light is reflected until it reaches a certain angle, referred to as the critical angle. Then the light is finally able to escape at the end of the cable and exit as a light spot, but at no other point in the cable. To learn more, students build a simple fiber optic light and a light effect with a crank for producing changing colors. Communication via fiber optics is also touched upon by building an optical Morse telegraph, and the use of glass fiber cables for global communication is discussed. The final activities performed with this set center on optical illusions, including the creation of a mechanically operated illusion, as you will see on the screen here. And that's the optics set. Once again, the set is recommended for 1 to 2 students per set. The next set we're going to look at is the Physics 1 version 2.0 set, which uses various track-based and roller coaster style models to explore the idea of dynamics, or processes involving motion. This set includes 780 parts in all, along with instructions for building 7 different models. The set includes a password for accessing PDF versions of teaching and activity materials, which can be downloaded directly from the fischertechnik e-learning portal. The first model in the set is used to perform some basic experiments to explore the relationship between force and dynamics. Students learn about the definition of force, which is the equation force equals mass times acceleration. And they learn how force is measured in newtons, named, of course, after physicist Sir Isaac Newton, who first formulated the basic laws of motion. The second model has students working with two different track shapes, where one is arched upwards and one is arched downwards, so that they can explore whether the path that an object must travel has any influence on the motion. They will discuss how the answer to the question of which track would be faster, referred to as the Brachis-de Crone problem, was originally solved back in 1696 by mathematician Johann Bernoulli. They will learn about Bernoulli's findings that the fastest curves are those referred to as cycloid curves, which arch downward. Students will also learn about the force which caused the metal balls to move about these arched tracks, that force being, of course, gravity. The next model used will begin the experiments with a looped track, so that the physical effect known as centrifugal force can be explored and discussed. The next group of experiments using a half-pipe model focus on energy, specifically energy of motion and the energy of rest, which are also known as kinetic energy and potential energy. Students learn how a ball at rest on top of a table has more potential energy than a similar ball on the floor. The experiments with the half-pipe model are used to introduce students to the law of conservation of energy, which states that energy can neither be created or destroyed, but only transformed from one form to another. Students also learn about James Prescott Joules and how the energy we use in our everyday lives to run, to walk, and even to think is measured in kilojoules and kilocalories. Students learn about concepts such as how the energy of the balls in motion can be converted into heat, or thermal energy, which is considered waste energy because it can no longer be used. They also learn about the three different classifications of friction: static friction, sliding friction, and rolling friction. Further experiments with a half-pipe model and several balls are used to demonstrate the concept of elastic collision, in which one ball connects with another ball and transfers kinetic energy to it. The effect of energy passing through the balls is called impulse, which is calculated by multiplying the mass of an object by the velocity it is moving at. The law of conservation of impulse is also addressed, which states that the impulse always remains the same, even in the event of a collision. Students will then build three different larger-scale obstacle course models with the various concepts they have learned about will all come into play. All three courses include an elevator system for continuously moving the balls to the top of the course. Some of these models include special effects which must be adjusted properly to starting the balls in motion. And each of these adjustments are clearly spelled out. Obstacle Course 3 is the largest of the models in this set, and it incorporates an automatic crossover combined with a barrier, a slash teeter-totter, and also a loop. And that is the Physics 1 version 2.0 set. The next set, Pneumatics, focuses on generating motion and accomplishing mechanical work with the use of air, specifically with compressed air. The set contains 440 parts for building 7 different models. The teaching and activity material, in this case a printed booklet that's included inside the box, is designed to accompany the set, first touches upon the history of pneumatics. And it goes back to the original pneumatic systems used by the ancient Greeks over 2,000 years ago. Students will learn that all pneumatic systems are actually made up of 5 different subsystems. One for generating compressed air, one for distributing the compressed air, one for conditioning and filtering compressed air, one for generating motion with the pneumatic cylinders, and finally, one for control of the motion with the use of valves. Students learn that the compressed air can be generated by several devices, one of which is the diaphragm pump, which is used in this set. The diagram here shows how this compressor fulfills that function. The compressor unit is fully enclosed in a blue housing, which is slotted like many of the fischertechnik parts to allow for easy attachment in the building of the models. The compressor unit is enclosed and maintenance-free, but will require a power supply, and in this case, you're going to need either a 9-volt battery or the use of the fischertechnik AccuSet, which I mentioned before, and that's a rechargeable battery pack with the charging unit, and they're sold separately if you'd like those. The compressed air for the simulation models that will be built is distributed by a series of blue hoses, which transport the compressed air from the compressor to the valves and the cylinders. Now, normally, as we mentioned previously, the next step in any industrial setting would be to condition the compressed air. This process would include such steps as filtering, cooling, dehumidifying, and adding oil to the air. For the simulation models that will be built with this set of course will not be required, but again, students are taught that this would normally be a vital step in the process. The next step is the generating of motion with the compressed air, which occurs with the use of pneumatic cylinders. Students learn that there are two different types of pneumatic cylinders: single-acting cylinders and double-acting cylinders. The two different lengths of cylinders included with this set, which the students will work with, are both double-acting, meaning that the cylinder has two different hose connections at opposite ends, along with a movable piston rod and piston with seal. When air is blown into one of these two connections, it causes the piston to move in the same direction as the air is being blown. As such, the piston has an active function in both directions of motion. The piston rod can be extended as well as retracted by the air. On the other hand, though, a single-acting cylinder would only allow the piston rod to be moved in one direction by air, while a spring would be required to move the piston back in the other direction. In any case, students will perform a series of experiments with the cylinders to help understand these concepts better. The way the pressure can be gauged is discussed, as well as calculating pressure. Students learn about the equation for calculating pressure, which is pressure equals force divided by area, referring to the fact that pressure depends upon the amount of force exerted on the round surface of the object. The final of the 5 subsystems of a pneumatic system, that being the control of the flow of air to a pneumatic cylinder, is then addressed. This is done with the use of valves. Valves can be actuated in several ways, either mechanically, electronically, pneumatically, or manually. The valves which are included for use in this set are manual, and students will learn how these valves are used. With this background in place, students can then begin to build the models, performing some experiments with each to fully understand how everything works. They start with the scissor lift model, first developing an understanding of how the lift functions, and then experimenting with the types of weights which can be hoisted. They will also add a second pneumatic cylinder to the model to see the effect this has on the types of weights which can be lifted. Next, students will build a balloon pump. They will perform various calculations, such as determining how long it takes the compressor to fully inflate a balloon, how much volume the balloon takes up in liters, and determining if a balloon full of air weighs more than an uninflated balloon. A double sliding door model is used to better understand valves. The set also includes instructions for building several models simulating those which in real life would use hydraulic instead of pneumatic systems. Students learn that hydraulics differ from pneumatics and that hydraulics use oil instead of air to cause the cylinders to move. In any event, these models provide more engaging opportunities for students to experiment with and understand valves, cylinders, and performing work with air. And that's an overview of what you can do with the pneumatic set. The next set in the STEM Fundamentals series is the Green Energy set. This set teaches students about the creation, storage, and the use of energy from the renewable sources of water, wind, and sunlight. The set also includes a reversible fuel cell with integrated hydrogen storage unit for creating models powered by this cutting-edge technology. The set includes 380 components in all, and instructions and activities for building 19 different models. Students will begin with a brief discussion of the disadvantages of sourcing energy from fossil fuels, such as natural gas, oil, and coal, as well as the problems associated with generating electricity with nuclear energy. They will contrast this with the advantages of instead using renewable sources. The reasons we need energy will also be touched upon, as well as how energy is measured. The first building exercises will focus on using water energy. The innovation of the water wheel will be discussed, and students will build a simulation of a water-driven hammer mill. They will then learn about the disadvantages of this form of water energy use. Next, students will build a water turbine and harness the mechanical energy generated by the flow of water and convert it into an electrical energy to power an LED light. The next group of model students will focus on using the power of the wind. The first model they build, a windmill with a pump, focuses on converting kinetic energy into rotational energy. The next model is a wind power station. This time, instead of converting the kinetic energy of the wind into mechanical energy, such as help to drive the pump, it is used to create electrical energy with a generator. The focus of the projects next moves on to solar energy. And here, students learn how a solar cell, also known as a photovoltaic cell, is used to convert this radiant energy from light, such as sunlight, directly into electrical energy. The principle of conversion is referred to as the photovoltaic effect. Students learn how solar cells are made of silicon, which has been sliced into very thin wafers or disks, and contaminated with impurities to cause an imbalance in the silicon structures. This process produces two layers in the silicon, a positive P layer and a negative N layer. The electrical current is produced by electrons from the N layer becoming excited by the light source and moving through a connected load, such as a solar motor, to reach the P layer. The more light that is cast on the cell, the more mobile the electrons become. Students build two different models, a ventilating fan and a merry-go-round simulation, both incorporating a single solar cell. They then experiment to determine the brightness of light required to make the motors turn, as well as measuring the voltage generated. In the next group of experiments, a second solar panel is added to begin work with a parallel connection, where more current is produced at the same voltage. The models of a bike rider simulation and a merry-go-round share a similar mechanical setup. Both utilize a belt drive, although the merry-go-round also incorporates a worm gear, which results in a slower motion. The next models using the solar panels focus on vehicles which utilize a series connection, where the concept is flipped, and now more voltage is produced with the same current. A push-button switch, or touch sensor, is also incorporated. First, a solar vehicle is built and experimented with. And because such a vehicle cannot function without direct sunlight available, the next experiments revolve around creating a solar charging station for an electric vehicle. This time, the vehicle is equipped with a gold cap energy storage unit so that it is able to function for a period of time even in the absence of such sunlight. Measurements of voltage, speed, and how long the vehicle can run on a full charge will then be made by the students. The concept of inverse parallel connections is introduced next, with a pair of models where the plus pole of the first solar model is connected to the minus pole of the second module. This concept allows for the creation of models such as a solar barrier that can open and close, or a solar tracking device which aligns itself to the sun. After this, students build an eco-home, which ties together many of the concepts addressed in the previous experiments and models. Following this, students will begin to work with a fuel cell, where they can learn how hydrogen and oxygen can be produced from distilled water, with the hydrogen then being used to power variations of the models previously experimented with. Enhanced versions of models, including a new solar charging station, a solar vehicle, and an enhanced eco-house using 3 solar panels, are built and experimented with, as well as fuel cell-powered vehicles. Finally, a solar pump with a fuel cell is built and experimented with to demonstrate the parallel connection of a fuel cell and solar modules. And that's an overview of the green energy set. The final set we're going to look at today is also the newest member of the fischertechnik STEM Fundamentals line. And this is the hydraulics set, which shows students the basic principles behind the use of pressurized liquids to perform work functions. This set contains 500 pieces with instructions for building 5 educational models. It includes full-color step-by-step printed instructions, and once again it includes access to downloadable teaching and activity materials from the fischertechnik e-learning portal. The teaching materials begin with an explanation of the term hydraulics, which is essentially the science of the flow behavior of liquids. Several of the benefits of using hydraulics are discussed, such as you see listed on the screen now. The origins of hydraulics are briefly discussed, focusing on the Brahman press, the first hydraulic press powered by water pressure, which was created by Joseph Brahman back in 1795. Now, working according to the hydrostatic law of Blaise Pascal, this enabled a piston to be pressed and the resulting power to be multiplied. Students learn how since the mid-20th century, hydraulics have found wide adoption for use in agricultural machinery, as well as heavy equipment such as excavators and forklifts. Next, the 4 subsystems of hydraulics are discussed: liquid storage, liquid pressure generation, liquid distribution, and the generation of movement. Students learn how each area will be addressed in the set, such as the use of hydraulic cylinders to generate movements with liquids. The simplified version of a hydraulic system used in this set is discussed. We start with a look at the control cylinder, which in many cases is the first cylinder. This is the cylinder filled with liquid. In this case, it'll be filled with water, which when pressure is exerted on this cylinder, the water, or the liquid, is squeezed out of the cylinder to flow through a connected hose into the next cylinder in the progression, a water tank, or to flow into the open. The use of a latch bar to fix the control cylinder at a desired position is discussed. Without this locking of position, whatever was being moved by the hydraulic system, such as the arm of a heavy excavator, would return to its original position as soon as the control cylinder is released. Next, the control cylinder is discussed. The control cylinder is mostly empty and retracted at the beginning of the process, but as pressure is exerted on the control cylinder and water flows from the control cylinder through a hose, the working cylinder is automatically extended and filled with the liquid. Students also learn the process by which they will fill their fischertechnik cylinders with water prior to their own initial experiments. Students build their first model, which helps to physically illustrate the differences in compression between gases, such as air, and liquids, such as, of course, water. Using the models shows that by comparison, the air can be easily compressed, while the water used can barely be compressed at all. Essentially, this means that the force exerted on the control cylinder is transferred directly, 1-to-1, to the working cylinder. The calculation of force using the equation of force equals area times pressure is also discussed. The next model that students will work on is a lifting platform, such as could be encountered in an automobile repair shop. And here, students perform experiments with 2 variations of the platform, one using 2 sets of control cylinders and work cylinders, and one using a single control cylinder attached to 2 working cylinders. Here, students can observe how in the second variation, less effort is used to cause the lift to move upward, but twice the power is needed to move it up is required to move it downward. The reasons for this and the different power ratio of 1 to 2 is discussed. The next model of a scrap baling press or a car crusher shows an example of how a telescopic cylinder can be used to overcome a distance greater than the length of a standard cylinder. Here, the telescopic cylinder is simulated by linking two cylinders together. Students then build two additional models for further demonstrations of hydraulics in action, a snowplow and a crawler excavator. And that's a look at the fischertechnik hydraulics set. And that concludes our overview of the Fischertechnik STEM Fundamentals line. Now, I'd like to mention here that we also have webinar presentations focusing on the Introduction to STEM series, the standards-focused project-based curriculum-centered STEM Prep 2.0 and STEM engineering sets, the robotics competition set, which also features standards-focused project-based curriculum, and finally, we have a webinar providing an overview of our various robotic-focused teaching solutions, and that includes the sets designed for entry-level exploration in grade school, on up to our fully assembled industrial simulation and training models that are used in higher education and vocational training classes. And of course, you can visit the Studica.com website to see the complete schedule for all upcoming webinars, and of course, to sign up and reserve your spot. But at this point, I'd like to open up things in case anyone has any questions. So as I mentioned before, if you do have any questions, if you'd like to, you could do one of two things. If you click on the little word balloon icon, second from the left in the Join Me toolbar, there's of course a chat window, and you can feel free to type any questions you might have in there. I will also open up the phone line in just a second here, in case you have any questions.
Everyone can talk now.
And if you'd like to, everyone is now unmuted, so you can go ahead and ask me in real time, or you can type it in the chat window, whichever works for you. Well, if no one has any questions, since no one is asking and no one seems to be typing, we're going to wrap this all up then. I'd like to thank everyone for taking the time to attend today. I appreciate it. I know that everyone's very busy. I will mention, for more information, if you'd like to get more information, if you would like to request a quote, or if you'd like to speak with one of your dedicated educational representatives, you can call us directly. Our number here is 888-561-7521. If you'd like to see our offerings on the website, you can go to www.studica.com/fischertechnik-education. And you can also email us. There are two email addresses up there. If you have general questions, you can email us at info@studica.com. Or if you have a question for me directly, if you'd like me to go over anything, or if you have any questions about anything Fischertechnik related, you can feel free to email me directly. That's my direct email address, Lance Z, Lancez, @Studica, STUDICA.com. So I'd like to thank everyone for taking the time to attend. Once again, we look forward to seeing you at future presentations, and we hope you have a great day. Take care.
Only the host